Okay, so we were talking about bonding, and we were talking about sort of Lewis structures last time, and obviously we started drawing some Lewis structures. Remember that when we draw Lewis structures for covalent compounds, we want to make sure that really the most important thing, or one of the most important things, is the total number of valence electrons there are in that particular molecule or ion that you may be drawing. Remember that the valence electrons equal the group number. So again, everybody in 1, 2, 3, 4, 5, 6, 7, and 8 all have the appropriate number of valence electrons for that. Once you do that, you want to think about, again, the logical arrangement of how things are attached. Remember that it should be the least electronegative atom that's in the center. You typically, again, don't find hydrogen in the center or fluorine, because fluorine is the most electronegative, and hydrogen, again, as we talked about, should only have really 2 electrons, so it should never find itself in the center. Once you have the logical arrangement, how many total electrons? Remember that if you do have something with a charge, you need to adjust the count on the electrons. So if it has a negative charge, you need to add some. If it has a positive charge, you need to obviously subtract some. What you want to do is make one single bond from the center atom to each of the outside atoms. Remember that each single bond is 2 electrons. So you want to figure out how many electrons you've used and take it away from your total. All the leftover electrons go on the outside atoms in pairs until they meet the octet rule. Obviously, unless it's hydrogen, then you shouldn't put any dots around it. If you do fill up all the atoms on the outside with electrons, and you still have electrons that you need to put onto the molecule, then you go to the center atom and you also put them on there as dots as well. At that point, you should be out of electrons, I would hope. The last thing that you want to check for is whether or not everybody has sort of met the octet rule, except for obviously hydrogen. And it's really at that point, it's a good rule of thumb that if somebody does not meet the octet rule, that you should try to fix it by putting a double bond. It's kind of use all your double bond options. Remember that, like we did here, when we make a double bond, like we see at the top left there, we're actually going to be bringing electrons in to do so. When you do that, that maintains the correct number of electrons you need for that molecule, and it hopefully should fix the problem. If it doesn't fix the problem and you have no more options for double bonds, then you would want to technically move to a triple bond, and it works the same way. We bring in the electrons to make that extra bond to do so. If you do that, you should at that point hopefully hit the octet rule for everybody that's there. In a case like this, which was carbonate, there could be multiple options where you could make the double bond happen. And again, in the case up here, we could go to the top, we could go to the right, or we could go to the left. What that creates is what's known as resonance structures, which are really sort of different versions of Lewis structures for a compound where you have more than one option, for example, to make that double bond. And it's because those double bond electrons are technically kind of moving around. So at any given point in time, they may be to the oxygen on the right in this example, to the top, or to the left. So all 3 of these, the true structure is probably somewhere between all 3 of these. So if you do write a resonance structure, you do typically use those arrows headed in both directions between them to indicate that they are resonance structures. But again, if you're just asked to draw a Lewis structure, you could just draw any one of the 3 and it would be good. Also, a reminder that anything that has a charge, typically you do put brackets around it and sort of the charge on the outside. Any questions on any of that stuff there? All right, so why don't we do a few more examples here, some Lewis structures. So why don't we draw this guy, this one, and that one. Okay, let's take a look, see how everybody's doing here. So we'll start with the SO2 first. So remember, pretty much one of the first things you want to do is figure out the total number of valence electrons. So sulfur is group 6 on the periodic table, so there's 6 for that. There's 2 oxygens, which are also group 6 there on the periodic table. That's going to give us a grand total of 18 valence electrons. In this case, we got 1 sulfur and 2 oxygens, plus sulfur is below oxygen on the periodic table, so it is less electronegative. So logical arrangement should be the sulfur in the middle with the oxygens on the outside in this case. Again, the least electronegative there in the center. We're going to do one bond from the center to each of the outside guys. That's going to take up 4 electrons. It's going to leave us 14 more to go, and that's going to go on the outside in pairs. So that is 2, 4, 6, 8, 10, and 12. At this point, I have distributed 16 electrons. I actually still have 2 more electrons to put on there, and they would actually go to the center atom in a pair of electrons. And that is how we get to the center atom there in a pair. Now, at this point, I have now put up 18 electrons, and obviously each of the oxygens are good. They each have 2, 4, 6, 8, but it is a sulfur in the middle there that's a little bit short. It only has 6. So again, this is a point where we would make a double bond. We could do it on either side. So we're going to take a pair of electrons and bring them in to do so. That would then give us a double bond here on the left. That looks like this. This is also one, obviously, you could draw a resonance structure for as well. And that would be a double bonding it to the other side instead. Here we are still maintaining our 18 electrons by bringing those electrons in to make the double bond. And now everybody has 8 around it, 2, 4, 6, 8 for that oxygen, sulfur 2, 4, 6, 8. And then the oxygen on the left there also has 2, 4, 6, and 8. Any questions on that particular one? So you should follow the rules here like we just did, and that will put those dots on the central atom. Again, you don't want to double bond or triple bond out of the box and not have the dots there because technically it is wrong for SO2. Should have those non-bonding electrons on the central atom. Any questions on that there? Okay, then we'll look at SO4 2 minus next, which I think is here. So SO4 2 minus. Once again, we got 6 for the sulfur. There are 4 times 6 for the oxygens, and we do have a -2, which means it has gained 2 electrons. So we do want to add the 2 to our total here. That is a lot there, 24, 26, 32 electrons here. Once again, sulfur being less electronegative should be in the center. We'll do an oxygen on each side. We'll do a single bond to each of the oxygens there. We have now used 2, 4, 6, and 8 electrons. We got like 24 more to go. That's going to go on the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. 22 and 24. At this point, we have put up all 32 electrons. Everybody has 8. This is an acceptable Lewis structure here for SO2. Again, put a little bracket around it with the charge on it. Any questions on that one there? All right. The next one that we had was SH2, I think. So SH2. Once again, sulfur 6. There are 2 hydrogens, each is 1, which is 8 valence electrons. In this case, should be sulfur in the middle, as hydrogen should never be in the middle. We're going to do a single bond to each of these guys. And at this point, obviously, we have 4 more electrons to go. We do not put on hydrogen because pretty much hydrogen is done at this point with the 2 electrons that are there. We then go to the center atom. And we put our dots there. So that is 2 and 4. That's going to give us a grand total of 8 total electrons. Sulfur in the middle there has 8, and each of the hydrogens obviously has 2, which is exactly what we have. Again, a reminder that hydrogen should always look like this, pretty much aligned to it, never dots, never double bonded, never triple bonded, nothing like that to hydrogen. Should always look like that, should always be on the outside. Any questions on that one there? All right, last one I think we had there that I circled was N2. So that is 2 nitrogens. So in terms of valence electrons, that's 2 times 5, which is 10 valence electrons. Now, in this particular case, this is a diatomic molecule, so there really is no center atom here, but we can just kind of do the same process. We'll just put them side by side, our nitrogens. We'll still follow the kind of the same rules. We're just going to connect it with one line, which gives us 2 electrons, leaving us 8 to go. So we'll go 2, 4, 6, and 8 electrons. At this point, we have now put on 10 electrons. Are they both okay? The nitrogen here on my left is not good. It only has 4 electrons, right? The other one does. So we could try to fix it by making a double bond. So we'll take our 2 electrons and move them in. And when we do that, we will end up with something that looks like this. Well, we got better here on the left. We're now up to 6 electrons, and we still have 8 on the right, but we're still not good. So at this point, there's obviously no other place that we could do a double bond. So obviously, we would go to a triple bond, which works the same way. We're going to take a pair of electrons here and again bring them in to do the triple bond. So we'll take these electrons right there and bring it in. The result of that is our triple bond that we see here on nitrogen. And here, nitrogen 2, 4, 6, 8. Nitrogen here 2, 4, 6, 8. Again, they both have 8. And we have still the grand total of our 10 electrons. Remember, making double bonds or triple bonds, we need to bring those electrons in. You can't just add electrons or add bonds. Otherwise, you'll end up with way too many electrons. Any questions on any of those or how to draw Lewis structures here? Once again, if you sort of follow the rules and stuff that we've been talking about, you should pretty much end up with a pretty good picture. Again, you don't want to kind of do piecework like we talked about last time, where you just kind of try to take the number of valence electrons, try to figure out where everybody goes. You'll usually end up with the wrong number of electrons and wrong number of bonds and stuff like that. Any questions? Okay. Reminder, please put your drinks away. No food or drink out in lab. So when we do draw sort of, when we do draw Lewis structures, sometimes, there could be different options as to maybe how you might want to attach everybody, or you might want to look at it and go, hey, maybe I do want a double bond or triple bond. So one thing that we started to look at is what is sometimes referred to as the formal charge. And the formal charge is basically the difference between the valence electrons in sort of the free atom and really the number of electrons, sort of how it's being shared in the Lewis structure when it comes together. To calculate the formal charge, we take the formal charge is equal to the number of valence electrons in the free atom minus the number of non-bonding electrons. Those would be the dots in your Lewis structure, minus 1/2 the number of bonding electrons. Those would be the lines in your Lewis structure. And what this will essentially give you is, for maybe a lack of a better description, kind of the charge that that atom is taking on within that Lewis structure that you drew. So it sort of gives you the individual sort of charges that everybody sort of takes on in a particular bonding situation. When you add up all the formal charges, typically it will equal the overall charge on the molecule. So, if the guy is neutral, then it should add up to 0. If it has some type of negative charge or positive charge, you could do that to get to whatever the overall charge is. So if we look at something, say like this is ozone, and we draw a Lewis structure for ozone that looks like this, we could actually assign formal charges for each of the oxygens that are here. So if we start with our double bonded oxygen, which is our guy right here, the formal charge would be the number of valence electrons in oxygen, which is 6. The number of non-bonding electrons in that particular oxygen, which is 2 and 4, minus 4. Minus 1/2 the number of bonding electrons. So there's a double bond. So each line represents 2 electrons. So that's 1/2 of 4 in this case. Again, 2 electrons here, and 2 electrons there for bonding. At this point, we got 6 minus 4, which is 2, minus a half of 4, which is 2, which means the formal charge on the oxygen that is double bonded is taking on a formal charge of 0 in this particular case. Any questions on where the numbers came from? Now we could do it for the other atoms here, which happens to all be oxygen. We'll do our single bonded oxygen at the right-hand side. And it looks something like this. And if we do it for that, the formal charge here would be 6 because there's 6 valence electrons in oxygen, minus the number of non-bonding electrons, which is 2, 4, and 6, minus 1/2 the number of bonding electrons, which is this guy right here, and that would be 2. So that is 6 minus 6, which is 0, minus a half of 2, which is -1. So in this arrangement, this oxygen over here is taking on a more -1 sort of charge, while the oxygen on the left there is taking on kind of a 0 charge. And we could do it for the very last oxygen there, which is the center guy, and he has like a double bond coming in. It's got some dots and a single bond coming out. And if we do the formal charge for this guy, it would be 6 minus 2, which is our non-bonding electrons, minus 1/2 of our bonding electrons. So that is 2, 4, and 6 electrons right there. That gives me 6 minus 2, which is 4, minus a half of 3, half of 6, which is 3, gives us a +1 overall. So although in this particular case, every single element that is there is oxygen, because of the way they are bonded, because of the way they are sharing the electrons, they each actually take on a different sort of charge in this sort of association. The guy on the right there, -1, the guy in the middle, a +1 charge, and a guy on the left there, 0 formal charge. Overall, if you add up all the formal charges for ozone, it is +1 and -1, which equals 0. So that equals the overall charge that we see there. So again, if you were to quote formal charges, they should have the pluses and minuses. So 0, -1, and +1. So if you're asked to calculate formal charge, you do want to make sure you include the plus or minuses with the numbers. Question on that one there. Okay, so why don't you try one here? Why don't you calculate the formal charge of every element in carbonate? Take a look. So this one we drew earlier. So we'll start again with our single bonded oxygen. And it will come out pretty much the same here. So we're going to have 6 for the oxygen valence electrons. In this case, we have 2, 4, 6 non-bonding electrons, minus 1/2 our bonding electrons, which would be the line here, which would be 2. That's going to give us 6 minus 6 is 0. And then we have half of that, which would be -1. So each of these single bonded oxygens are -1 in terms of their formal charge. Like obviously the guy on the left will come out the exact same. And if we do our double bonded oxygen there, once again, the formal charge here would be 6 minus our non-bonding, which is 2 and 4, minus 1/2 of 2 and 4 there. Going to give us 6 minus 2, which is 2, minus half of 4, which is also 2, and that would give us a 0 formal charge there for the double bonded oxygen as before. By the way, as you can see, it doesn't matter which it is in. If it's a single bonded oxygen like that, it will always be -1. Double bonded oxygen will always be 0. Now, if we look at the carbon, which essentially is double bonded up on top and single bonded on each side, for carbon, it actually has 4 valence electrons. And in this case, there are no non-bonding electrons, so no dots on the central atom there are this carbon. And minus 1/2 of 8, again, 2, 4, 6, and 8 electrons happening there. That gives us 4, basically -4, which is 0 in this case. So in this particular case, both the carbon and the double bonded oxygen are taking on really a 0 formal charge. And the -2 overall for carbonate is actually associated with the 2 single bonded oxygens, one on each side in this particular drawing. Any questions on how to calculate formal charge? So in addition to sort of calculating formal charge, it is actually helpful, and we do use formal charge to help us decide, like I said a second ago, sort of, is this Lewis structure maybe a better structure than this Lewis structure? And again, you can get some different Lewis structures depending on how you put things together. Maybe if you want a double bond or triple bond in certain cases. So ideally, in terms of formal charge, the best sort of structure is like where you can pretty much get everybody to 0. So if you have some type of formal charge where kind of all the elements or a good majority of the elements end up with a 0 formal charge, that's sort of your ideal situation of what you would be looking for. If you have Lewis structures where you end up with formal charges of like 2s and 3s and really high sort of values, those are probably not as likely to occur than where you can sort of minimize the formal charges on the elements. And if you have to sort of choose between maybe 2 different Lewis structures and you want to use formal charge to help you to do so, like I said, 0 is pretty much optimal. But the most plausible structure, the one that's probably the better structure, would be where we have the negative formal charge on the more electronegative atom. So if you have sort of 2 structures which are sort of equivalent, you calculate some formal charges, and you end up with a really kind of higher positive formal charge on the more electronegative atom, that's probably not going to be your sort of best option. So in using formal charge to help you decide between different sort of structures, and this is what formal charge can be helpful to do so. Like I said, 0 is sort of your best, mostly 0, low formal charges. And again, if you have sort of ones where you end up with the more positive charge on the more electronegative, that's probably not the best structure. So to help us kind of look at this, if we took something that was like CH2O and maybe you weren't sure how it should be connected, maybe you roll with these 2 possible connections here and you draw the Lewis structure. So take a second, calculate the formal charge on each of these, and based on formal charge, which structure would be the better structure of the 2. So take a couple minutes, and again, calculate the formal charge to help you decide which one should be the better structure of the 2. Okay, let's take a look. So we'll call the guy on the left there number 1, the guy on the right number 2. So let's take a look at number 1 and calculate some formal charges for that guy. We'll start with the single bonded hydrogen. That is 1 for hydrogen. It has no non-bonding electrons. It has 1/2 the number of bonding, which is 2. That is going to give us a 0 for the formal charge of this hydrogen and that hydrogen as well. If we look at the carbon there in that first one, it looks something like this. So it would have 4 for carbon, -2 for our non-bonding electrons, -1/2 of 6 for our 3 lines there. That's going to give us 4 minus 2, which is something that is 2, minus 1/2 there of 6, which is 3. So that's going to give us, I believe, a -1 happening here for that carbon. And lastly, our oxygen in this guy, first one, looks like a double bond, and this and that. That's going to give us a 6 for the oxygen, -2, minus 1/2 of 6. That's going to give us 6 minus 2, which is 4, minus 3, which is +1 in this particular case here for that oxygen. Any questions on any of those calculation there for that one? We'll do the same thing here for number 2 to get an idea of what we're dealing with there. So obviously the hydrogen will come out the same as here, and it would be 0 and 0. Again, it would be 1 minus 0 minus 1/2 of 2. In this case, we have a carbon that is single bonded and then double bonded there. And that would give us a formal charge for it of 4 minus 0, minus 1/2 of 8, which would also be 0. And lastly, our double bonded oxygen there would be 6 minus 4 minus 1/2 of 4, going to give us 0 like it did before. So in this case, we got zeros for everybody there. Number 2, which one would be the better structure based on formal charge? It should be number 2. Number 2 has minimized formal charge to 0, which is like the most optimal thing that you could have. The guy on the right does have some formal charges. They are small formal charges, but the problem also with the guy on the left there, on the left there has the smaller formal charges. Problem with it is we see actually on the oxygen, which is more electronegative than the carbon, the oxygen actually has a more positive formal charge, which is not ideal either. So that's not a great situation there. So again, if you had to choose between the two, the guy on the right should be the better Lewis structure based on formal charge. Any questions on that there? All right, so since people like to make double bonds and triple bonds based on formal charge, which one would be the better structure for CO2 here? Take a look and see. So we'll start down on the left here. So once again, we can see our double bonded oxygen, which we've seen a couple of times at this point. And as you maybe have noticed, it always should come out the same. So it's going to be 6 minus 4 minus 1/2 of 4. And that is going to give us a 0. So we got a 0 there and a 0 there for each of those. We then have our carbon in this case, which is double bonded on both sides. And it would be 4 for carbon minus 0, as there's no dots there on carbon, minus 1/2, 8, as each line here represents 2 electrons, also going to give us 0. So that's pretty hard to beat there with all zeros all the way across. Let's take a look over here at this guy. We have our single bonded oxygen, which we've also seen before, going to give us a formal charge of 6 minus 1/2 of 2. And that is going to give us a -1. So this guy has a -1 formal charge. The carbon in this case is single bonded on one side, triple bonded on the other side, giving us a formal charge of 4 minus 0 minus 1/2 here of 2, 4, 6, 8, going to give us a 0. And lastly, our triple bonded oxygen, which is rarely seen, is going to be our we'll go this way here. Formal charge there. 6 minus 2 minus 1/2 of 6 in this case, going to give us 4 minus 3, which is +1 in this case. So clearly here it is the double bonded guy, which would be the better structure here. So this is why in certain cases, you shouldn't double bond something or triple bond something. Double bonds are sufficient. Again, the purpose of bonding really is to the best idea is to kind of reduce down the formal charge on everybody to more of a 0 type of situation. So sometimes what you get into when you're using formal charge to decide between different structures is like, this is a better structure than this one. This is maybe not the best structure and stuff like that. Any question on how to use formal charge to help you decide? Yeah. All right, so we talked a little bit about resonance structures earlier when we were drawing them. Let's talk a little bit about bond length, and obviously you don't need to memorize these numbers, but these are the bond length for different types of bond, really kind of single, double, and triple bond. And if we look at something like carbon, the single bond's 154, the double bond's 133, and the triple bond's 120 picometers. The general trend that we see is as you continue to put on bonds, the distance between everybody gets smaller. So as you bring those electrons in to make a double bond, kind of pulls everybody in closer to each other. When you make the triple bond, it kind of pulls everybody even closer into each other. We also see that with nitrogen and carbon. Single bonds 143, double bonds 138, and the triple bond is 116. So every time you add those bonds, again, it's just bringing those electrons into the center. Those more electrons in the center is going to be attracted to each of the nucleuses and kind of bring everybody tighter into each other, and the distances between them get a lot smaller. How that relates to strength is a triple bond is typically stronger than a double bond, which is stronger than a single bond. They're not like a double bond is twice as strong as a single bond or anything like that, but that's sort of the general trend. And I think about it like a pencil. If you have a brand new pencil right out of the box, you could just snap it pretty easily. You take a couple of chemistry exams and you erase a lot. You got like a nub and an eraser left. Very, very hard to try to break that thing in half because everything is tight. Everything's in close to one another. And that's what we generally see with bond strength and bond length. Now, obviously, we talked about electronegativity, so we'll kind of roll through this here. We did it a little bit earlier here. And those are our breakdowns for our different types of bonds that we talked about. Remember that we do use electronegativity differences to help us determine, is it a polar bond, which means unequal sharing of electrons. And again, up to about 0.4 of a difference in electronegativity helps us do that. We also, anything above 0.4 to below 2 is a polar bond, which means unequal sharing of electrons. And again, anything to 0.4 is nonpolar, equal sharing of electrons. And anything above 2 was ionic, as we did before. So here, again, looking at our electronegativity values, 0, as we also talked about, again, sometimes referred to as being purely covalent, which is nonpolar as well. And that's like perfect equal sharing of electrons. Again, unequal sharing of electrons here in our HF. And as we also talked about last time, right, creates a sort of charge separation within the bond where the side that's more electronegative is partially negative, the side that is least electronegative in a bond is more partially positive. Remember, we also could draw those bond dipole arrows where it points to the more negative side and that to the more positive side to indicate that separation of charge as a result of unequal sharing of electrons. As we also talked about last time, again, a reminder that these are partially positive and partially negative because the electrons have not fully transferred. So they're still hanging on with some degree of sharing, which is why they're only partially. And that's different than what we see here in our ionic bond when we do get the complete transfer of electrons from the metal to the nonmetal, and we get a full positive charge and negative charge because those electrons have completely transferred. So once again, no sharing of electrons here and some aspect of sharing of electrons happening on those two guys. All right. That does bring us to bond dipole moments. Again, bond dipole moments are when we talk about our dipole moment, is basically the idea that there is some type of separation of charge. And we represent bond dipoles a lot of times with that arrow, as I drew just a second ago. And that is what is sometimes referred to as a bond dipole. A reminder that when we look at electronegativity values or the difference in electronegativity values, it really does answer, for the most part, just a simple question of, when we put these two elements together, or atoms of these two elements, will they share those electrons equally? Will they share them unequally? It really does not tell us in a lot of cases whether or not the overall molecule is going to be polar or nonpolar. Will the overall molecule share the electrons equally? The only place where bond polarity and molecular polarity basically are the same is actually in a situation like this where we have a diatomic molecule. And that is because, frankly, this bond right here is a polar bond. And it's the only bond in this entire molecule, which means that this molecule would also be polar as well. So there's two types of polarity, and we're going to talk more about molecular polarity in the next chapter. But bond polarity is simply just talking about these two atoms. Are they sharing it equally or unequally? Molecular polarity is taking every single bond you have in the entire molecule, and overall, are the electrons being shared equally or unequally overall? And that's what molecular polarity is here. That's basically what this is. And again, the one place, and really the only place where they basically are the same, is when you're dealing with diatomic molecules, just two atoms, because there's frankly only one bond that is there. Any questions on that there? All right. So a case of something like Cl2, which has just one bond, it's just the two Cl's together. That is a nonpolar bond. It would not have a dipole moment. something like this, which is, again, all these guys are simply two elements together. The difference in electronegativity for each of those tells us that it's going to be a polar bond for these two. And because this is a diatomic molecule in each of these guys would both be polar molecules as well. This would be a non-polar molecule, because, again, the Cl bond is non-polar, and that's the only bond there. This obviously would be ionic with that big of a difference between those two, right? A difference of 3 would give us an ionic bond. And as we talked about before, pretty much that metal, non-metal is all you need to see there to know it's ionic. So no sharing of electrons here, unequal sharing of electrons there, and then obviously equal sharing of electrons up there on the top. Any questions on any of that? So again, in each of these cases, because they're diatomic, it will also tell you whether or not the overall molecule is polar or non-polar as well. All right, so we did some of those. So let's talk a little bit about bond energy, which is kind of the only energy we're going to talk about here. And it is not table 8.2, so don't worry about that. So when we have bonds, or when we really have a chemical reaction, there's basically two things that happen. Because all chemical reactions are electron-based, pretty much on the left-hand side, which is our reactants, we pretty much need to break all the bonds that are there on the left-hand side. And when we get to the right-hand side, which is our products, we need to make all of those new bonds. Remember that it is conservation of the elements. So again, if we started with 4 carbons on the left, we should have 4 carbons on the right-hand side of the arrow. They may be in different compounds on the right-hand side. Now, as we talked about before, there is a much more energy required to break a bond that is triple bonded versus double bonded versus single bonded. We could calculate the energy for this reaction, which is the enthalpy, which we might have talked a little bit about, which is known as delta H. That is the enthalpy. That is the heat of a reaction. And we really can calculate the delta H for a reaction based on what is sometimes referred to as bond energy, or bond enthalpy is sometimes referred to. When we break bonds, is it endothermic or exothermic? Remember, endothermic means that we need to put energy in. Exothermic, we need to remove energy. So when we do break bonds, as it says up there, it is going to be endothermic. So you have a bond and you put energy in, everybody gains energy, they wiggle away, and they're able to break apart from one another. When we actually want to make bonds, everybody's kind of moving around a lot. They need to lose energy or give off energy, which is exothermic. They kind of slow down, and that allows them to kind of come together and make the bond. So making bonds is exothermic, releasing the energy, and breaking bonds is endothermic, which is absorbing energy. That means that pretty much when we break all these bonds, all the energy values should be positive numbers. So I think we talked a little bit about energy, and energy values that are positive numbers are endothermic type values. It means they're absorbing energy. Breaking bonds or making bonds which are exothermic will all be negative values for energy. Negative values with energy indicates that energy is being released. So like we talked about with the energy, with the waves and all that, those values will end up being negative as the energy is being released. So we could calculate the delta H for this reaction by taking the bond energies. By simply, you can add up all the bonds that you're going to break on the reactant side, and then add them to all the energy it takes to break the bonds on the product side. So there is a table that obviously would be provided for you like this, and we could look at it and look up values. So when you're doing this type of calculation, it's really important to know sort of what everybody looks like. So sometimes you may need to kind of sketch the Lewis structure really quickly to see, okay, am I dealing with single bonds or double bonds or triple bonds? That's obviously going to give you some different values when you come to this table. As you can see there on top, nitrogen single bond, double bond, triple bond. So you want to come to a table like this knowing exactly what type of bond, single, double, or triple, that we're dealing with. So let's say we took CH4 and Cl2 like we have up there. And if we draw these guys, we have CH4, which looks like this. That's an H down there. We have Cl2, which looks like this if you quickly sketch it. And it's going to go to this guy on the other side. And then we have HCl. So if this is the reaction that we're doing here, everybody on the left-hand side, we pretty much need to break all those bonds. So if we take a look here on the left-hand side, we have 1 carbon-hydrogen bond that needs to be broken, 2 carbon-hydrogen bonds, 3 carbon-hydrogen bonds, and 4 carbon-hydrogen single bonds that basically need to be broken. So basically, we're just going to kind of take a little accounting of everything. So we have 4 of the carbon-hydrogen single bonds that need to be broken. We obviously have 1 chlorine-chlorine single bond that also needs to be broken. And this is pretty much everything that needs to be broken, right? And we could go to that table that we have on the other side and look up those values. So if we look up for we had 4 of the carbon-hydrogen single bonds that need to be broken. So we're going to take 4 times 414 from that. So 4 times 414 kilojoules. And that's for all the carbon-hydrogen single bonds. We also had a chlorine-chlorine single bond, which is, where is it at? Right there on the bottom, right there, I think. And that is 243 kilojoules to break that bond. So we have 1 of those guys going on. 1 times, I'm getting old, 243, that's good. 243 kilojoules. So if we add all that together, this is all the energy required to break all the bonds that we have on the reactant side. And it looks like we end up with 4 times 414 plus a 243. It's about 1,899 kilojoules of energy needed to break all of those bonds. And that would be a positive number, as it's endothermic, to put all the energy in there to do so. Any questions on where I got any of those numbers from? We're going to do the same type of calculation for our product side, except that we're making all those bonds. So we just need to add up everything that we're making on the right-hand side. We have 1, 2, and 3 carbon-hydrogen single bonds we're making. We also have 1 carbon-chlorine bond that we're going to make. And we have 1 hydrogen-chlorine bond that we're going to make as well. So that is everybody that we're making on the right-hand side. So if we add up all that, we would have 3 times 414 kilojoules for the carbon-hydrogen. To look at the carbon-chlorine, which would be here at the very bottom, it is 339 for that guy. So we got 1 of those, 1 times 339 kilojoules. And lastly, we have a hydrogen-chlorine bond, which would be right here at 431 kilojoules. Now, if we add all that together, we end up with 3 times 414 plus 339 plus 431. That's 2018. But these are all the ones that we're going to make. So those are exothermic. So really, everything here should be negative to indicate that it is releasing energy. So it should be negative 2018. Let me write it up here, negative 2018 kilojoules. So the overall delta H would be found by basically just adding these two numbers together, our 1,899 kilojoules to break all the bonds, our minus 2018 to make all the bonds. So if we do all that good stuff and punch in the right numbers would be good. Our delta H for this reaction would be plus 1899 plus minus 2018 kilojoules, going to give us a negative 113 kilojoules. Negative 113 kilojoules tells us that overall, based on bond energy, is this reaction endothermic or exothermic? This reaction is exothermic because overall the energy change is negative. So overall, the result of making and breaking those bonds is going to give off an excess of a minus 113 kilojoules of energy when this process takes place. Question on how to calculate all that there. Okay, so why don't you try one here and see how you do. Let's do, that's what we just did. Hopefully they end up. So let's do, why don't you do this one here? So it's H2O2HO. I'll write it up here so you have it. It's maybe easier to see. So we have H2 plus O2 gives us some peroxide here. I think that's what we got going on. Yep. All right. So calculate the delta H for this reaction. And is it endothermic or exothermic? Take a look. So once again, we're going to break everything on the left-hand side there. So we are breaking one hydrogen-hydrogen single bond, which would be this guy, 1 times 436. We're also going to be breaking one oxygen-oxygen double bond. And once again, if you're not sure, it's a good idea to draw the Lewis structure to make sure you're getting the right type of bond. And it also helps you visualize all the bonds that are there. It's very common when people do this and they just take the kind of equation with not drawn, they miss some center bonds and stuff like that. So just helps you visualize everything. So we're looking at oxygen-oxygen double bond, which went right there. So that's going to be 1 times 498. And again, this is going to be all of our breaking of bonds here. So that's going to give us a grand total here of 436 plus 498. Looks like a 934, and that is going to be positive as it is endothermic to break that. Going to our product side, we are going to make an oxygen-hydrogen bond there and one right there. So we're going to make 2 oxygen-hydrogen bonds, which is right there. So that's 464. And again, like I was just saying a second ago, sometimes if people don't draw this, they will forget all about the center bond here. And again, we are making an oxygen-oxygen single bond that's going to happen there. And that looks like, where's that at right there? 142. And that is obviously all the ones that we are making in this case. So 2 times 464 plus 142 gives us about a 1070 kilojoules. And once again, this would be negative since we are breaking these guys exothermic and releasing. Overall, our delta H here would then be 934 plus negative 1070. Going to get us 934 minus 1070 minus 136 kilojoules, which once again tells us that this reaction is also going to be exothermic based on bond energy. Any questions on how to use this or that type of stuff? Now, if you did have some coefficients, which could happen in a balanced equation, you could have some coefficients, you do need to take it into play. So obviously not in this case, but let's just say, for example, there was a 2 in front of it, like 2H2 or something like that in the equation. You then would obviously have to double it, right? Because you would then have 2 HH bonds that you would be breaking. So if you do have any type of coefficients, you would need to take those into account in terms of what you are making. Again, I would recommend in that case also just drawing as many there would be. So just draw the two so you can see the two bonds that you're either making or breaking in that case. So if you do have coefficients, you do need to take them into account, obviously, when you're doing this and adding up everything that you're breaking. Because if you had 3 of them, you would be breaking 3 of those type of bonds that you would have there. Any questions on that there? Okay. All right. Good, it agrees. All right. So we did talk about resonance structures, and once again, we did a little bit earlier when we were drawing. It does occur a lot with double bonds, but it's pretty much any opportunity where you can either double bond or even in some cases triple bond, or have other options as to where to do that from. And then obviously we've done these guys before, so we'll kind of go through that. The benzene ring, by the way, is an organic compound, and it's basically 6 carbons. It's oftentimes drawn like this. Each of the little points here are carbons. And it also has actually 3 double bonds in it, like this. Or you could draw it this way here, where the double bonds go this way. And there would be 1 hydrogen at each of those carbons. And sometimes you'll see benzene drawn like this with like a little circle in the middle. And that's because those double bond electrons are moving around, as we talked about, like the other ones, the double bonds. So sometimes they'll just kind of simply draw like a circle in the middle to indicate that those electrons are moving around. All right, let's get this guy here, get the idea. So the last thing we're going to talk about here in this chapter are exceptions to the octet rule. Now, there are several exceptions to the octet rule. The first exception to the octet rule is one that is referred to as being an incomplete octet. And much like the name implies, it means it actually is perfectly fine with less than 8 electrons around it. For the most part, that's your boron and aluminum, although aluminum really doesn't show up too much in covalent bonding. So for the most part, it is like boron is the most common one that you'll come across. So something like BF3 here, the boron in BF3, when we just look at the boron here, it has 6 electrons, and it's perfectly fine with 6 electrons. It is sometimes what is referred to as being electron deficient, as it has less electrons. It is something that will be able to accept electrons relatively easy, because it is sort of missing it, but it is perfectly fine with that. So like I said, in most of our practice, boron is the one that you'll see the most that could do that. Technically beryllium and aluminum, but those are really sort of metals. So you don't really see them pop up all that much, but you know, they technically can kind of have an incomplete octet and be okay with that. But I would say boron is the most common incomplete octet that you'll sort of come across. Another exception to the octet rule is one that is referred to as a odd electron molecules. And these are guys that pretty much, because they have odd number of electrons, you end up with an unpaired electron. These guys are sometimes referred to as being like free radicals. Maybe you've heard of that before. Chlorine does that a lot in atmospheric chemistry. They are typically a lot of times very, very reactive because, frankly, they have 1 unpaired electron. So they kind of want to fix that problem. So they're kind of very, very reactive. NO2 are examples of that. Again, you actually end up with an unpaired electron on the nitrogens. I would say maybe a little less common come across in a class like this, the odd number of electrons, but that is, you know, an exception to octet rule that could occur. The third exception to octet rule, which is pretty much the exception that we see the most, is what is referred to as the expanded octet. The expanded octet means there are certain elements that are perfectly fine going over 8 electrons. They could go like 10 or 12 electrons in that case. And those are the expanded octet. Pretty much on the periodic table, if you find sulfur, and you go to the right and to the left and down on the periodic table where sulfur is located, and we're talking about nonmetals pretty much below there and to the right and left. Those are guys that have the ability to do the expanded octet. That is because sulfur is on period number 3 of the periodic table. Period number 3 would represent the N is equal to 3 level in terms of electrons, electron configuration, quantum numbers. What orbitals are found on the N equals 3 level? There are s orbitals, right? There are p orbitals, and that is the very first level where we first start to see what orbitals? The d's occur. That's the very first level where we actually see the d orbitals occur. So because sulfur, and again to the right, left, and down, have the d orbitals available to them, although they may not be using them themselves, that gives them extra places to stash kind of the extra electrons to go above 8. So technically anybody below there and below can go above 8. That also means, though, if you look at something like carbon, nitrogen, oxygen, and so forth above them, which is in period number 2 on the periodic table, that is N is equal to 2, which means on the second energy level, there's only S and P orbitals available to them. Those guys can never, ever, ever go above 8 because they don't have the d orbitals available to them. They do have to basically maintain the octet rule for sure. But again, once you get into that sulfur and below, they can go above that. Any questions on that there? Now, if we look at something like SF6, it would look something like this. I won't draw all the dots on the fluorine, but there's dots all the way around all those fluorines. Maybe I will draw it just to be good, I guess. All right. But for our conversation here, looking at the sulfur in the middle, it has 2, 4, 6, 8, 10, and 12 electrons around it, and it is perfectly happy doing so. Any questions on that there? So incomplete octet, less than 8, pretty much boron's the one that we would come across most likely. Odd number of electrons, again, probably not going to come across too much of those, but these for sure. The expanded octet, sulfur and down, has the ability to do so. Doesn't mean you need to do it all the time. It doesn't. It just means, it has the ability to do so. Why would that be important? Well, it sort of ties into what we were talking about a second ago about formal charge. You could come up maybe with a situation where you might want to actually double bond something to reduce down the formal charge. So for example, let's get draw it here, I think. If we look at SO4 2- that we drew earlier, and we drew it earlier sort of obeying the octet rule, and we ended up with a picture that looks like this. Now, if you Google SO4 2-, which you should never do, you should learn this stuff yourself, by the way, you might actually see it drawn something like this, with some double bonds happening there. So this is a situation where they're both really acceptable structures for SO4 2- or sulfate, but we can use formal charts to help us understand maybe which one would be a better structure. If we calculated the formal charge for our guy on the left here for our oxygen, our single bonded oxygen, we would have 6 - 6 minus 1/2 of 2, which means we would end up with -1. That means each of these oxygens here have a -1 formal charge, as they're all exactly the same. If we did it for our sulfur in the middle, which basically has a single bond all the way around, that would be 6 - 0 minus 1/2 of 8, and we would end up with a +2 charge, right? Our +2 formal charge on the sulfur in the middle. Overall, if we add up all of our formal charge on the guy on the left, that's +2 -1 - 1 is 0, -1 - 1 is -2, so it does add up to -2. It's an acceptable sort of structure here. But now, why did some people double bond it? Let's see if it actually makes it any better here. If we look on the right, our single bond would end up the same as to the left there. So 6 minus a half of 2, which would be -1. So once again, these guys would carry a -1 formal charge, the single bonded oxygen. Our double bonded oxygen, like we see before, will be 6 minus 4 minus 1/2 of 4, which is 0. So this guy here and this double bond would end up being 0. And now our sulfur in the middle, which has gone to an expanded octet, would end up looking like this. It would be 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12 gives us a 0. Based on the formal charge, which one in this case is actually the better structure? It is actually the one on the right. Yeah. So even though we followed our rules like we did before and we came up with a pretty good structure, which is what we have on the left, the one on the right is definitely a better structure, and why you oftentimes when you do Google it, we'll see it drawn like this. And if you drew that in the previous class, they would know you Googled it because you shouldn't have ever drawn it like that, by the way. So we have minimized the formal charge on really 3 of the elements, right? This oxygen on top and bottom have now formal charge of 0, which has minimized it. And the major improvement is also on the sulfur, right? It went from like a +2, which is not the greatest, to a 0 formal charge, and it's really sort of made it a much better structure. So again, if you were to have to choose based on formal charge, which one should be the better, because sulfur is able to take that expanded octet and take in some more of those electrons, it really does sort of lower everybody's sort of formal charge overall and makes for a better structure that you see there. Now, not in all cases, right, making the extra bond does that. We saw that with the triple bond versus the double bond, right? With the CO2, by making the triple bond, it actually didn't make it a better structure. The double bond was a better structure to look at in that case when we talk about CO2. Any questions on that there? Okay, let's take a peek, see how we're doing. We'll start with the first one there. So we'll just follow our normal rules here. We'll do some valence electrons. So phosphorus is group 5, and there's 4 chlorines. Each is 7. We do have a negative charge here, which means we do want to add 1 more. So 28, 29, 34 valence electrons. In this case, it is going to be the phosphorus is going to go in the middle. Phosphorus and chlorine are in the same period. Phosphorus is least electronegative. Chlorine will go around. We'll do our same move here, a single bond to everybody. That is 2, 4, 6, 8 electrons. Then we'll go on the outside. So that's 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. At this point, we have filled up all the outside ones. We actually still have electrons to go. Those will go on the center atom just like normal as a pair of electrons. Here we see phosphorus. It will end up actually with 2, 4, 6, 8, 10 electrons. Again, expanded octet. It could do it because it's right next door to sulfur on that 3rd energy level. So again, it does have the d orbitals to allow it to do so. So phosphorus is okay like that, and then all the chlorines have still met the octet rule, so they are also still okay. Any questions on that one there? Looking at the next one, which is xenon, and some 4 fluorines. Xenon is actually the noble gas, so that is group 8, plus 4 times 7 for our fluorines. That is 28, and 8 is 36 valence electrons. By the way, the value of the electronegativity for the noble gases is like 0, pretty much, right? Fluorine is the most electronegative. Noble gases are chemically inert, right? So they don't want anything. They're happy the way they are. They're not going to bring any electrons. So if you ever has to think about which one's the least electronegative, you know, noble gases sort of are thought of having 0 in terms of electronegativity value because they're really not wanting to bring any electrons towards themselves. That means obviously xenon would be in the middle, plus we cannot put fluorine in the middle since it is the most electronegative. Doing our same move there, we're going to do a single bond to each of these guys, which gets us to 8. We'll continue on the outside. So 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. In this case, we actually still have 4 electrons that need to be placed. Once again, they will be placed on the center like we did before in pairs. So a pair there and a pair there will work. And this will now give Xenon 2, 4, 6, 8, 10, 12 electrons. Once again, it is below sulfur, so it can handle doing so. All the fluorines there have met the octet rule, and we have placed our 36 electrons up there on our picture. Obviously, another expanded octet in this case. Any questions on that one there? All right, lastly here, we have our phosphorus, which is 5 plus 5 times 7. That is 40 electrons. That's going to be a phosphorus in the middle. We're going to do a chlorine on the outside. And wherever you want to put that 5th one, I'll go up on top. We'll do a single bond to each of them. That is 5 bonds. That's going to be 10 electrons, leaving us more to go on 30 on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. That should be 40 electrons on that guy. Everybody has met the octet rule. Phosphorus, once again, has gone the expanded octet, which is okay in this case. So I know after they beat into your head, probably never go over 8. We will do a lot of going over 8 in this class. So we will do a lot of expanded octets. We will see, we talk in the next chapter about geometry, some geometries that go with these expanded octets. So that we'll see some of these geometries that occur. Any questions on how to draw stuff that go above 8? Now, clearly, if the instructions say obey the octet rule, you should not go above 8. Yes, so unless necessary. In this case, it would be necessary. In all these cases, you cannot really obey the octet rule with how many electrons that you have. Any questions on drawing Lewis structures above the octet rule? All right, so if I'm not mistaken, I believe that should wrap